Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Getting into space is loud. There's no way around it. The controlled explosion that propels a spacecraft into orbit generates a lot of noise. Anyone who's ever watched a launch in person knows how true that is. But sound can have a very detrimental effect on the spacecraft riding on the rocket. Sound is nothing more than a vibration, after all, and shaking things often leads to breaking things. And that's why acoustic testing is such an important part of evaluating a spacecraft's fitness for flight. One of the companies at the forefront of acoustic testing for spacecraft is MSI-DFAT. And my guests on this edition of the Ex Terra Podcast are Alessandra Alex Carrella, Max Myers, and Bradley Hope from the company, who are here to shed some light on the topic. Gentlemen, welcome to the program.
Good morning, Tom.
Let's start out with each of you briefly introducing yourselves and your roles at MSI-DFAT. Who wants to go first?
I'll go first, sir. My name's Bradley. I'm a U.S. Business Development Manager. You'll often see me at a lot of the trade shows and industry events all over the country, and sometimes even internationally. We just got back from Italy a few weeks ago at IAC. It was one of the biggest events in the space industry, and we had a great time there.
Max?
I'm Max Myers. I am one of the system technicians. I am also the lead uprigger, which means that I help set up all the systems on site. And I also help perform the acoustic test as well as maintain all the systems while we're in the shop. And I also run and help develop our website with Brad.
So in the music business, you'd be the chief roadie, I guess.
Yeah, yep, exactly. Yep.
And Alex, what about you?
Hi, Tom. My name is Alessandra Alex, and I work in the management and engineering and sales and marketing. I'm a VP of strategy and growth, so anything to do with taking the company forward and making sure that in 5 years' time we are strong as we are today, and creating new technology and new business.
So then give me a brief history of Maryland Sound International.
A brief history of MSI starts. MSI starts in the 60s when Bob Goldstein, the owner and president, started to create amplifiers and audio engineering for entertainment and music. Carly Simon, Pink Floyd, he did a lot of people. He produced a lot of there is more platinum discs than satellites in our. But that was back in the 60s. And then for what concerns the space business, in 1998, there was a program called QuickScat that NASA was developing together with Orbital. And there was a test requirement, and they wanted to. So the idea of using loudspeakers is back in 1966. It was the first paper that the idea was put out there. Never happened because of the physics. Current going through a coil heats up, and the efficiency was very poor. They couldn't get to the levels. So it was not until 98 that there were enough technology advances to start looking at this opportunity, this idea of using loudspeakers. So we went there, we did a test, we ran a test, and it was as loud as 134 dB. Mm-hmm. But the field was not as diffuse as it should have been, as uniform. So we had to work on it. So we had a lot of feedback from NASA, from the customers, from the engineers, and eventually we slowly started to add automatic control. So we had one drive, so one signal going to all the speakers, and eventually we ended up in 2008 with a MIMO solution. So we had multiple output and multiple microphones, so multiple speakers sending out different independent signals, and multiple microphones telling us what was happening. And so there was some maths behind, and in 2019 there was another update on the controller, and now we basically 25 years later and 230 satellites qualified later, we are able to produce an acoustic field which is as close as it gets to that of a reverb chamber.
Now, the FAT part of the name, MSI-DFAT, that stands for Field Acoustic Testing, correct?
Direct.
Okay,
Direct field acoustic testing.
Direct field acoustic testing. So what does that mean, and how did that part of the company evolve from MSI?
So one of them, over the first part of our DFAT activity, so from 98 to 2016, we were using off-the-shelf speakers, and we were using the same components that entertainment people were using. So that we call it upstairs and downstairs, but the DFAT team in 2016 basically span off to dedicate itself to space testing. I mean, going to a space lab requires cleanliness, requires specific calibration, and so we didn't want to use, we didn't want to mix things. So in 2016, we span off, and we have our own inventory, our own trucks, our own people, and so that's how the DFAT span off from the entertainment people.
Now, explain to me what acoustic testing means in layman's terms.
I'm a layman, so I could probably answer that one.
Tag, you're it, Bradley.
Yeah, this is always a fun one, and it's a very common question whenever my friends or family ask me, what do you do for a living? And I say, we do acoustic testing, and they say, well, what is that? And what does that mean? So the reason why you need acoustic testing for the first place, just like in the introduction, is we're essentially recreating the very harsh noise and vibration environment created by sound during rocket launch. That's a very violent environment, and it's part of an overall series of tests that they call environmental tests that a spacecraft will go through prior to launch. So typically you'll go through different types of vibration testing where you mount mechanical components or assemblies on shaker tables and shake it. You'll put it in an oven and bake it. And usually around the last one in a series is the acoustic test. So the jet engines or the rocket engines emit a very loud sound. I think the SLS was somewhere around 200 decibels, if I remember correctly, of the external noise environment. So if you look at any rocket launch, one thing that you'll notice is often there's big pools of water underneath the launch pad, and that collects and absorbs a lot of the sound energy. So that sound energy is not all captured by that pool of water, but helps dampen down some of that response. The rest of it, as it launches, there's several different environments that it goes through, and that acoustic energy vibrates up into the structures. So the sound or the airborne acoustics translates into structural based vibrations and can affect and break and damage different parts of the rocket. So the environment that we are recreating most typically is the one that's inside of the fairing. So all the external noise comes into the fairing. There's some lessening of the amount of acoustic energy, so that 200 or so decibels outside of the rocket turns into about 150 inside the fairing. And just to give people a little bit of a reference scale, I think a lawnmower is around 80 decibels, a rock concert's around 100 decibels, and then you start popping eardrums around 130, and 150 is fatal to humans. So your organs and parts of your body would resonate until it would become fatal to you. So it's a very, very violent noise environment. There's other applications that we do besides just recreating the fairing, but 90% of the business is testing a satellite or a space telescope or the fairing itself or any part of a rocket or a payload that's getting launched into space.
And I don't think people actually realize if they've not been to a launch, and the only one that I've actually been even close to was the very last shuttle night mission. And my wife and I drove down to Canaveral National Seashore, which is probably 4 or 5 miles north of the Space Center. And we watched, and of course, night turned into day when the rocket actually, when the shuttle actually lifted off. And 5 or 6 seconds later, we got our insides shaken. I mean, it really, even from that distance, and so you explained kind of how loud the rocket launch is and things that it can be compared to, but then has acoustic testing always been a part of the spacecraft certification process?
Yeah. So acoustic's always been since the Apollo days. They've built these they call it reverberant chambers. These are mega facilities with 3 feet thick walls. They use gas, nitrogen gas, so they have liquid nitrogen that is made gaseous and fill the chambers with it to reduce sound absorption. So they can do a lot of tests in those rooms. But as you can imagine, the amount of money to build one and to maintain one is extraordinary. So, there are some big facilities. NASA owns a few of them, and some a major company, Lockheed Martin, Boeing, they do have these facilities built in the 90s, 80s. So they have these facilities, but they are sparse around the country. So you can imagine that, if you want to test and you want to go across the country, there's a lot of money involved, and mostly the risk. I mean, anything can happen once you're on the road. And if anything happens, you are in for a long engineering exercise to see if anything happened to the spacecraft. So you don't want to do that. Hence DFAT.
Max, I want to bring you into the conversation as well. Tell me what it takes to actually set up for one of these tests. As Alex was saying, sometimes there are specific facilities for that. Do you always do that in a specific facility, or can you do that someplace else?
So the whole goal of DFAT is that we can go to your facility and set up in pretty much any room that fits our system. So obviously you don't want to bring the whole goal is to not have to transport your article out of your facility to, get rid of those movements, because the more you move your spacecraft, the more you're going to cause issues. So we can come into your high bay, come into somewhere within your facility, and what that would cause would be we bring in anywhere from 2 to, usually 2 is the minimum amount of trucks. Anywhere from 2 to 8 is the most amount of trucks we've brought on a test so far, but we have tests spec soon that are going to be up to 10 to 11 trucks worth of gear. And we come, and between anywhere from 1 to 7 days, we set up a system, and everything is modular. So a client will tell us what size their article is. They'll tell us the diameter. They'll tell us the height of their article, and then the level. And then we will perform a structural analysis, number one, based off of the location in the country or wherever the test may be, because we can go overseas as well. So we'll figure out what seismic zone they're in. If it's somewhere like California, we have extra rigging precautions to make sure that, we're fitting within those seismic parameters. And then from there, once we have that, we can go and figure out what the amount of speakers we're going to need is going to be. Are we going to need more low frequency? Are we going to need more high frequency? Are we going to need our standard setup? And then from there, we pick and choose. And then our in-house team here will prep everything, load it on trucks. And then we'll get a drawing from our engineer in-house of how we're going to set the system up. And then usually we'll take it on site. Once we're on site, we send, we have a crew of anywhere from like 5 to 10 people. And we bring it in, and everything is usually picked by a overhead gantry crane. Mm-hmm. And it's just stack, step, and repeat. And then we can usually do that process, like I said, between it's usually the average is 1 to 3 days, with 2 being our pretty standard setup time. And then testing is usually with simulator runs, testing, loadout, everything. We can usually be there between 5 to 7 days total. And then transport time on either end, depending where you are in the country. And I think that's a pretty good summary. Am I forgetting anything?
I don't know.
That was a question for Alex or Brad.
Yeah, that was a great overview. I think the only thing that I would add to it is just highlighting the efficiency of the team and the crew. Tom, you mentioned these guys are sort of like roadies, and Alex often compares them to being a race car performance team. So you ever watch NASCAR races and they pull into the pit and swap out the tires in a half second? You can kind of compare that as an analogy to what the team does when they go to set up these tests. We often ask our customers, how much time do you think it would take you to set up the test? And they'd be like, a month, 2 months. And we do that and condense it down into just a few days. So it's a very, very efficient team, and we're the best in the world at what we do.
We definitely don't like, we definitely like to keep it moving as quick as possible. And we have, we know our rig extremely well, and we like to keep things moving. And, our guys are trained to get the system up and down as fast as possible to remove that downtime on the article and the spacecraft, and especially in those rooms, because a lot of times those rooms at those facilities are needed for other things, because we're taking up an area that could be a transition room for loading trucks, or they're used for where I'm trying to think of examples of what those sometimes it's right in the middle of where they're doing vibration testing, or we could be holding up something depending on where the room is, or the spacecraft just needs to get from acoustics to thermal or something. So we want to make sure we're in and out of that facility. And quite frankly, we don't want to hold them up. So the best thing we can do is be in and out as quick as possible. So having our team trained to be as fast as possible is definitely something we strive to do.
So go ahead, Alex.
Yeah, I just want to something. So the facility that Max was talking about in the space business, they called AIT, so Assembly, Integration, and Test. So that's where satellites get assembled and then integrate all the different payloads and components, and then they test it. So the managers and technicians and engineers working in there are very careful and very anal about cleanliness, about things that they move, things that they and we've been doing this for 25 years, and believe me, that is the best thing. So there are the engineers that get the data, right? So they get the data of the acoustic test, like, oh, that's a very good test. But then we get called over and over, and we have emails of this engineer and this manager sending their congratulations and their thanks to the team, because they do it so professionally. They really love working with these guys. These guys go there, they don't knock anything over, they don't get anything dirty, and they are careful, they're professional, they're quick. And this is our, frankly, this is our best reconnaissance from the industry. So these guys are really welcome anywhere they go. That's something that I wanted to stretch.
My guests are Alessandra Alex Carrella, Max Myers, and Bradley Hope from MSI-DFAT on the Ex Terra Podcast. Take a moment right now to click subscribe to be sure you don't miss any of our podcasts, or if you're watching on YouTube, any of the videos from Ex Terra, the Journal of Space Commerce. I want to dig a little bit deeper into that. Do all spacecraft require acoustic testing? I know, Bradley, you and Alex both have obviously a manned spacecraft in your background, but we're talking about everything from something that size to, I would guess, CubeSats. Do they all need to have this kind of acoustic testing?
It's actually more of a question on several factors, one being also the surface area of the spacecraft. So, yeah, you have different categories, manned or unmanned equipment, and then the size of the equipment and the amount of surface area that it has. We have a pretty vast repertoire. If you go on our website into the photo gallery section, you can see just a sample of it. But we've tested everything from satellites the size of a dishwasher to objects, in the coming years that we're testing that are well over the size of a school bus, 60-foot tall tests. And that's one of the advantages of our test setup, is the scalability of it and the ability that we can fit the test to whatever the test article is. Alex, do you have any other thoughts on whether acoustic tests would be required or not?
Yeah, you're right. Brad is right that the acoustic loading that cause vibration is irrelevant for small things. So a CubeSat wouldn't be excited by vibration. However, for example, we had a meeting a couple of months ago. I was there and I was chairing this meeting together with NASA JPL, and one of the discussion we had was how in Europe and also NASA uses acoustic tests for workmanship. So workmanship is that test whereby you shake things off to see if there's anything coming loose. Shakers and other vibration tests, which are mandatory, a shaker's range ends about 2 kilohertz, 2.5 kilohertz, depending on the size, So anything above that, it wouldn't be excited. And that's why acoustic gets into play. So we can use acoustic for workmanship to make sure that no bolts and nuts and things come off loose.
From a technical standpoint, why do companies choose DFAT?
That's a good question. I call DFAT a business-driven technology. I mean, DFAT doesn't do things that the chamber cannot do. I mean, a chamber can do acoustic tests, so DFAT does the same. So from this technology was born out to save a lot of money. So, a program can save a lot of money. That's what DFAT was born. However, as technology developed, we are now finding out that DFAT has a potential of disrupting the way we test with acoustics, the way we do it. So our technology with MIMO, so with the centralized MIMO control, where we can control any point in the field, but also the relationship between these 2 points. So this gives us the possibility of replicating something that a chamber cannot do. So by definition, a chamber is a volume with walls which are no parallel, and it creates a field called acoustic fields, which are diffuse acoustic fields. With DFAT, the way we do it, we can create also non-diffuse acoustic field. So we can create a more realistic way. So what we're doing today, we are replicating what the chamber can do, but the potential of our DFAT solution is way bigger than that. And we are now publishing papers. There is one that we published at a conference at the European Space Agency in September. We are running an update for another conference in March in Los Angeles. So things are coming out, and I guess we are ready to improve and furthermore develop this technology that we invented 25 years ago. Things are coming.
So then, Bradley, I guess this next one is kind of for you. What are the business advantages or value propositions of using DFAT?
Yeah, absolutely. And Max kind of already highlighted on one of them, simply being you can save so much time or uptime. You can increase that on your spacecraft. So the program managers at our customers love us because if you're shipping the test article, say you have some large spacecraft like this crew module behind me, just imagine how you're going to transport that. There's multiple modes of transportation, truck, rail, boat. You can fly it with a helicopter or a plane. So that's expensive. And then depending on the distance, that transportation cost and time is massive as well. So if you cross state borders, there's all these regulations. You're going to need insurance. The insurance costs, we routinely do analysis to help our customers understand how much we can just save them on insurance. In one test, we saved just under $1 million on the insurance costs alone for customers transporting these very large and complex spacecraft. So as Alex mentioned, it's a business-driven technology, and that's really our value proposition is we significantly increase the uptime by decreasing the downtime by having just a 1 day or 2 day test window. And you can test in place, so there's no movement of the spacecraft required in most cases. You can use the same exact facilities as where it's manufactured, or we could go and fit to whatever the protocol is for testing in the assembly integration test workflow. So we've done tests at the launch sites, even at the last second, where a customer comes to us and for whatever reason, it just makes logistical sense to test, right at Cape Canaveral. So we can test indoors, outdoors, in permanent structures and temporary structures. As long as we have the ability to get in and access, then we can test from anywhere. So testing from anywhere is really a very good value proposition, and that's why our customers call us.
Max, this next one may be probably more up your alley just because you're the guy that's on scene. How often do things break during testing, and what are the protocols if something does break?
Do you mean in terms of like on a spacecraft or on our end? I mean,
the thing that you're testing, how often do you shake it apart?
So it's actually much less. It happens a lot less than people would think. Most of the time, it's just because stuff's built well. I mean, I've been on the road with DFAT in January, it'll be my third year with the company. And most of the issues we find are small issues. A lot of times will be small electrical, mechanical issues, but things falling off aren't issues. Most of those are kind of found with like vibe tables, where we can find we'll find things like things with G forces, stuff like that will kind of come up. But I'd say it comes up here and there, but it's not that big of an issue. This is more, if you have gotten this far, by the time you get to acoustic, you're going to kind of know where your issues are. But yeah, they'll come up every once in a while, but it's not like we aren't seeing, like reflectors and dishes and stuff fall off usually. Yeah, but we're not walking into the circle and seeing a screw on the ground. And if we did, I think that would be a big, it'd be a big
red
stop.
flag.
Yeah, big red flag. And I think the whole site would come to a stop. But usually if something like that were to happen, we usually come to a complete stop, and it's usually the system comes down and it's a complete reassess, and we come back for retesting. When the client's ready, it's usually not a pushback like, oh, we're going to put this back on and we'll retest in 2 hours or tomorrow. Mm-hmm. It's usually they're going to do a full recheck and figure out where the issues are, and we'll come back when they're ready. Because a lot of these people want to make sure that everything is right where it should be, and that, it's been rechecked, double checked, triple checked,
So in your planning then, when you get a new client, what steps do you take to ensure that the test doesn't damage the spacecraft or the satellite? Do you have specific things, a specific checklist that you go through to try and be as sure as you can be that you're not going to damage the test object?
Yeah. I feel like the best way that we can say that we start is we never start at full level. I feel like that's the best way to start. So when we start minus 12 dB under where our goal level is. So that's the best way to not damage anything. So since we're doing everything's going up at the same level, in a scale, right? So we're starting, if the test level is 144, we're going to start at, 132 of that test. And so they can see anything at that beginning level that's going to be an issue later. So if there's a reflector that's shaking a little bit, they're going to see that on their accelerometers very early, way before we're going to go up and hit that full level. So they'll see it we'll start at 12, and then we'll do a -9, -6, -3, full level, and then usually a post test that's going to show everything. So if there's an issue at -12, they're going to see it at -9, they're going to see it at -6, they're going to see it all the way up. So they'll know there's an issue way before we go to full level, which keeps us from damaging it. They'll see it before it gets too intense.
And just for reference too, whenever we're talking about decibels, it's not a linear scale. So -12 is significantly different from the full level test. It's actually a logarithmic scale. So every 3 dB is a doubling. Yeah.
Yeah. The difference between 132 and 144 is quite substantial.
And when I'm an audio guy, I know what a decibel is, but you might want to just explain kind of what that scale is for the folks who might not be quite as familiar with that audio term.
Yeah, Max or Alex, you got to talk about how the decibel was invented, and maybe
is the log of a ratio between the pressure measured and the reference pressure, which is 2 to 10 to the -5. So it's 20 times the log of the ratio. That's why it's not it's a logarithm scale, and so every 3 dB you double that pressure. That is how decibel are computed. One thing that I wanted to add about these, somebody call it de-risking, and then Max explained very well how we do it on the test side. Before going there, however, there is a team of analysts in the companies, in our customer, that they use simulation software to run what is called a vibroacoustic analysis. So they have different simulation tools, and we work with them to make sure we give them models and data so they can do this analysis even before we get there. I mean, the most advanced of these is called a digital twin. So, if you have heard this name before, it is a recreation on a computer of physical reality. So, they have a model of the structures, they have a model of the circle of the speakers, and they can basically run the test before we even get there. And so this is one way of de-risking it. And then once we go on site, then we also have these scheduled testing that goes from low level all the way to the full level.
You all mentioned a couple of times vibration testing, and I think it might be helpful to have folks understand the difference between acoustic testing, which basically shakes things, and vibration testing, which basically shakes things.
Exactly. We call it vibroacoustic testing. In fact, we call it vibroacoustic, and then we cover both. We cover. I think the difference is so if you look at this, there is an interesting chart that I usually use during my talks, and there is a frequency range difference. So there is vibe testing is structural borne vibration. So the spacecraft is on an adapter which is in the fairing, and so there's a lot of vibration coming through the base, and so there's a lot of base testing, base vibration, and there is, for example, ignition and all the initial part of the engine liftoff are covered by a sine test. So there's a sine sweep test that goes between 5 to 150 hertz. And then after that, there is 120 hertz. And then there is a random vibration test. So it goes all the way to 2 kilohertz. And then there's the acoustic test that covers up to 10 kilohertz. And then there is a pyroshock, which covers up to 100 kilohertz. So that is so the different tests cover different ranges of the live, the harsh condition at launch, all the way to shocks. The shocks, the pyroshocks. So there's a lot of pyrobolts, a lot of mechanism. Every time that a booster gets separated, when the spacecraft is released, there's a lot of shocks, and so Gs that can reach in the thousands of Gs. Up to 100 kilohertz. So those are different tests. So there are different tests for different frequency range and different part of the launch, and acoustic is one of them.
I got a notification from NASA late last week, excuse me, that they're looking now for proposals to lease their vibration testing facility at the Johnson Space Center in Texas. And I know you guys don't do vibration testing per se, you're acoustic testers, but does this kind of lead to maybe a thought that NASA might be looking to outsource more of this kind of testing so that they don't have to take care of? I mean, there's going to be a lot of outsourcing coming up, I think, during this next administration on a lot of things. Is that maybe indicative of one of those kinds of scenarios?
On the go ahead, Alex.
No, that was it, Brett. If you have
so just looking at the way the space industry is structured fundamentally, you had all of these incumbent agencies and historical traditional way that the whole ecosystem was set up, which was essentially disrupted by companies like SpaceX and all this new space wave. And so the competitive advantages of a lot of the historical companies are being undermined. And so they need to be as nimble as the new space companies now. And technologies like DFAT allow them to do that. So actually the crew module that's on Alex and mine's background was a NASA program through Lockheed Martin that we do every time they do an Artemis mission. So even though NASA has its own reverberant testing chambers, they're getting pressed more and more and constrained more and more on their budget. And so they're looking to save time and costs just like the rest of the industry. And so we've been able to see a benefit and a push towards technologies that enable our customers to have a bit more competitive edge, and DFAT is one of those.
Just Johnson, a couple of go ahead, Alex.
I just want to add that you mentioned Johnson. Johnson, for example, has an acoustic chamber, but as you know, there is it's been not running for a long time, and to put it back on is a lot of money. So these facilities are expensive to maintain, and so I wouldn't be surprised if they are up to reuse the facility for commercial purposes, because it's a lot of money to maintain them.
Just a couple of things more, gentlemen. And first of all, if you have any particular success stories or maybe a spectacular failure that you'd care to share. I see a lot of smiles.
Exactly. We have MSI-DFAT is success story. So we started, for four decades, MSI has been operating, and since 2016, when we have span off, we've been growing and we've been creating new technology. We're still making new speakers, new control strategies. It's a lot of for a niche. This is a niche environment, and so creating all these knowledge and all these technologies is a success story, definitely.
Are there industries besides space that require this kind of acoustic testing? Do you work with anything else?
Yeah, absolutely. We are hosting or trying to host some exploratory discussions in the coming year outside of our core market. So space is definitely the beachhead for us, and there's adjacent markets that we work with or are looking to work with. One of the ones would be automotive for applications like cabin noise and road noise, especially with the big push towards EVs. These are essentially sound sources that we're manufacturing and very familiar with using the technologies. We also work within aircraft with applications like jet engine noise, or I guess defense applications as well for technologies like missiles and warheads, which are essentially rockets, right? So there's a lot of anything that gets really loud and gets launched or experiences cabin noise is something that we would be interested to help with.
The MIL standard, which is the book of testing in the defense industry, there is a whole method called 515, which is called acoustic testing. There is so military have a whole books for it, and we work with them closely.
We are just about out of time, but I want each of you to do this, and this is one of the things that we ask all of our guests to do. And since I've got three of you, I'm going to ask all of you to look ahead of 10 to 15 years in space commerce and your role in it, and tell me what you see.
Hopefully, I'm still doing business development in some capacity in the space industry. If AI doesn't take over all the jobs. I on a personal note, I think it'd be really fun, and it's always interesting to see the evolution of the industry as a whole. There's some really interesting things that I think we haven't even thought of before, but with space tourism, there's collaborations like Hilton with the space station and making a space hotel essentially, or Prada with the astronaut spacesuit. And so you're taking a luxury clothing brand and making the next generation spacesuits out of them. So it's always very interesting to see how these the ecosystem evolves and all the relationships in it.
I mean, I just hope we, with everything with space exploration, going to Mars, going further out into space, and things only getting bigger, and the space industry the industry as a whole getting bigger. We get to just keep building bigger, badder, louder systems, and I get to keep putting them up. That's what I hope my role is. I just enjoy the challenge of it, and the more stuff I get to put up in the air, and the louder I get to make the system, turning that thing on and feeling it and looking at the client's faces as we hit 148, 149 dB is pretty cool. And getting to, and when someone walks in and sees that system 40 feet in the air around an article and they go, wow, that's a cool feeling. So to be able to keep doing that and keep going to new heights and keep sending out the loudest sound systems in the world would be pretty cool, and hopefully keep pushing the boundary of that.
As I think it was on Spinal Tap, crank it up to 11 and break off the knob.
Yeah, exactly.
With Max and Bradley, we're definitely going to be in business for a long time. We definitely, that's all true. I think that as Max, Max was hinting at something that is in the back of my mind. And as we go farther and farther, and people will travel. So, guys, to go back and forth from Mars is about 24 months. It's a long time. So there's a lot of human acoustics, and there is a lot of work going into modeling and virtual representation of a space environment. There's a company making haptic gloves so they can feel temperature, can feel roughness when they do, they simulate operation in spacecraft. There's a lot of that thing, and there will be some acoustics too. So we'll be working on more refined models, acoustic models, and there will be a human perception, human psychic experiments on acoustics, and the humming of flywheels. There's a lot of noise in a spacecraft. So there is I'm ready to get involved in some of those problems and solutions and finding solutions.
Very good. Well, gentlemen, we are out of time, but Alex, Max, and Bradley, thank you for joining me on the program today.
Thank you, Tom. It's been a pleasure.
Thanks, Tom.
Thank you.
Alex Carrella, Max Myers, and Bradley Hope represent MSI-DFAT. And that's going to do it for this edition of the Ex Terra Podcast. You can subscribe to the audio version of the podcast on Spotify, Apple Podcasts, Audible, and many other popular podcasting platforms. Be sure to click subscribe so you don't miss any of our podcasts or any of our other videos. You can get daily updates on space commerce by subscribing to the Journal of Space Commerce on Substack at www.xterrajsc.com. And one thing more, be sure to connect with us on LinkedIn and follow us on X at Ex Terra JSC. Until next time, I'm Tom Patton. Thanks for joining us.
I wanna go faster, faster. Hands in the air, we're gonna crash. Searching for the answers like Galileo. The proof is looking glass. That's for reason. Our dreamer's eyes we gaze into a sense of purpose known by few. Like finding water